Okay, welcome to PDE's lecture 13, I think it is. During the last lecture, we started talking about Green's functions, and we realized that a guy who was a baker and owned a flour mill in the Industrial Revolution created a new technique that even the professors at Cambridge could not. And it was a powerful technique in that you solve one problem and its solution permits you to write down a whole series of answers for similar problems where you can change the boundary conditions or you can change the forcing function. And so we're going to go on with that theory and look at it in the specific case of Laplace's equation. So just to remind you, what we did was we were seeking the solution to the Laplace's equation with a source, and we said that, or this is basically what we derived using the divergence theorem in the previous lecture, that you can write down the solution of this equation in terms of some function g which obeys the same equation except that it has a delta function source. So in some sense you construct the solution to this more general equation by the contribution of all the delta function sources under the integral sign. So here you have g is equals to the integral of the forcing function over the domain times the Green's function minus the Green's function times either the derivative of u with respect to n minus the derivative of g with respect to n times u. Okay, and we said that this is still entirely general, and then we looked at specific cases. For example, in the situation where you want Dirichlet boundary conditions, that is where you specified or you are given u on the boundary, you choose a Green's function that obeys this equation as well as a boundary condition. Remember, you needed a boundary condition and the equation for it to be well posed, but so you choose the boundary contribution to be 0, and then you got this expression. And since you can solve for g1 and the derivative of g with respect to n, then you have a unique solution. And we simply, a unique solution provided the forcing function u is known on the boundary. And then we looked at the second case, which are called Robinson boundary conditions. If you're given this combination, you can also do exactly the same thing, and you can find you find a different Green's function. Note that g1 and g2 are different because the boundary condition it has to satisfy is different, and we'll see examples of this illustrated in this lecture. And then the final case was mu equals to 0, and here is something tricky, and I'll illustrate what's going to happen here. Here is the Neumann case, but you actually run into a problem and you have to change the formulation slightly. So there's a similar formulation, but we'll also look at that in what comes. So the last time we also looked at the symmetric solution for G, and we argued that if G is just symmetrical about your, your source point, then you could show that 1 over 2 pi is equals to the ln of R, where that R is simply the difference between the source and the target point. So you have this R is equals to x plus y, where this big X is merely the coordinates that are now centered at x and y, and the difference between the two. So it was that very nice little picture that looked like this. So that the symmetrical solution is this situation. So this solution works only if you are on an infinite domain and in other special cases. And so what we're going to do now is we're going to find a way of actually using the solution to build up the general solution that satisfies not only the delta function, but also the boundary conditions. And it's a very cute thing. The main power about the symmetrical solution, this ln R, is that it captures the singularity point over here. Okay, so it's the solution that's very strongly peaked, usually at the point where the target and the source point are the same. Okay, so the way we force it to get to satisfy the boundary conditions. It's actually very cute, except the amazing thing is that Green thought it out for the first time. He sort of split the problem into the hard part and then the boundary condition. So the way you construct those G1 and G3 and eventually also G2 that I mentioned is you say, let our Green's function be the totally symmetric solution plus another thing, okay? And we choose this other thing so that it obeys the boundary, so that the boundary conditions are satisfied. So the first thing to note is that thing is a solution to the Green's equation, provided the Laplace of V is equals to 0 on D. And that is easier to solve than that equation, in fact. Okay. And it must be the Laplacian must be equals to 0, so the differential equation is solved. And what this does is it allows us to choose V so that on the boundary D, you get V to cancel out whatever the symmetric Green's function has imposed on the boundary. So it's sort of V kind of fixes the boundary condition, and it can always do so. Okay, so let's see how this works. Suppose we have a Dirichlet boundary condition. We're going to choose G1 equals to our symmetric solution plus V1. We're going to say on the curve C, which is the boundary, we're going to choose that V1 is equals to minus the ln of minus 1 over 2 pi the ln of R. So, and this is only true on the boundary. Inside, V1 is entirely determined by this equation, and we have our maximum and minimum principle, so all the big action actually happens on the boundary, and that's what is given by this expression. So it's cute, right? And the same thing when we were dealing with those Robin boundary conditions, we set G3, the normal derivative plus mu G3 equals to 0 on the boundary. And the way we do that is we say let G3 equals to the symmetric solution plus the ln of V3, and we then choose V3 so that the boundary condition is simply equals to the forcing function, or the boundary condition that results from the symmetric solution. So the two solutions cancel each other out, and that's how we choose V3. And once again, V3 is equals, the Laplacian is equals to 0 on the boundary D. Okay, and the very powerful thing is that once you have got, say, V1 or V2 for a specific domain and a specific boundary condition, sorry, V1 and V3 for a specific domain and a specific boundary condition, you keep it for the rest of time, and then you can solve any problem with a forcing term or source just by the equation on the previous slide. So there are books that actually list Green's functions, and they are useful to have if ever you are going to do physics or actually try and solve problems analytically. The people that do that are getting fewer and fewer because most people try and do numerics, but there are still some very, very cute solutions that you can get. I mean, the advantage of a Green's function is it allows you to sort of analyze the properties of the solution for any boundary condition, whereas if you do a numerical simulation, you're only going to get one instantiation for for a specific initial conditions. You're not actually going to be able to analyze the whole thing without doing a lot of computing. So there is an advantage to getting the analytic solutions, and there's a huge advantage when you start working with them abstractly. Like most of quantum mechanics that have all that bracket notation and that's closely coupled, or was closely developed using Green's functions, and the idea of generalized functions, actually. So Green's functions is one example of a generalized function. In fact, it's the generalized function that has the impulse response. Okay, but there's a more general theory that this thing eventually led to that people use. That's not the topic of this course, but it does exist. Okay, so let's now look at the final case namely the Neumann boundary condition. And I'll show you what the problem is first before I tell you what the solution is. So Neumann boundary condition, we're trying to solve that thing with du dn that is known on C. And we know from our uniqueness theorems that u is determined only up to a constant because we've only specified its derivative on the boundary. But there's also a thing now that is new here, is that there exists on C a constraint on du dn. We're not totally free to choose du dn. And the reason for that constraint is that if we look again at our Green's equation, right, we have that and we use the first expression of the Green's equation where that A that we entered is equals to the gradient of phi, or in this case, the gradient of u. We have that the Laplace of u is equals to the gradient dotted in with the normal term. So this is an additional constraint that appears only for Neumann boundary conditions, and it basically says that this function is known. So take in some sense, the sum or the integral of this function of the whole domain, it's got to be equals to the integral of du dn over the boundary. Okay. And so in particular, if we're looking at the particular case of the way we specify the Green's function for the other two cases, suppose we have the Laplace of g is equals to delta of the difference of the source and the field and the source point, and we try and specify this thing equals to 0 on the boundary, which would be your like default thing to do based on the other two cases, it doesn't actually work. Okay, and the reason it doesn't work is that we have this expression that the gradient of g ds is equals to the integral of, the Laplacian of g over the whole domain is equals to the gradient, the normal derivative of g on the boundary. And if we've set that thing to 0, we have that integral is 0. But now, if we do the other thing and we actually know that this Laplace g has been set equals to the delta function, we have a problem. Because the delta function, as long as r is in the domain, is always equals to 1. Okay, it's one of the definitions of your delta function is that the integral in which the 0 argument occurs is always equals to 1. So this is clearly a contradiction. Okay, so we must do something else when we actually are finding the Green's functions for Neumann conditions. And there's something else that we do, and so we're basically going to start from scratch again, derive our definition for the Green's function and then show that it works. It's not a big modification, but it's an essential one. We're going to say instead of defining our Green's function to obey just the Dirac delta function, to have that as a source, we're going to add a constant k. Okay, and that is enough to actually give us enough room that we can actually get a well-defined system. So we're going to say our Green's function is equals to as a delta function source plus a constant, and the derivative on the boundary is going to be equals to 0. And we're going to then integrate over the domain. And if we do that, right, you once again integrate this thing, it is equals to basically, here we go. Okay, you integrate the Laplace thing, of g, it simply equals to this, which is equals to 0 on the left-hand side. On the right-hand side, you're now going to integrate over the delta function, which is 1, plus the constant. You're just going to integrate over the whole domain, so it's a constant times the area of the domain. Okay, and you can now choose k so that it's equals to the 1 over the area of the domain, and then we don't have a contradiction and we have enough room to solve our problem. And what we then do is we have to do one more thing, because remember, it's determined only up to a constant, the uniqueness theorems, if you specify the gradient. And it would be convenient if you had a Green's function to have a unique definition, okay? Because otherwise you're going to have a whole bunch of textbooks saying this is one type of Green's function for the Neumann boundary conditions, and another batch of textbooks that give you another answer which is equally valid, but then if you start confusing the two, it leads to confusion. So they basically went about and they normalized it, and the condition that they normalized it with is saying, okay, this Green's function is not unique and it's determined up to a constant, but we're going to choose it, or we're going to remove this ambiguity by simply requiring that the average value of the Green's function is 0. Okay. So that then is a well-defined Green's function for the Neumann conditions, and so you have this extra condition coming in over here for your Green's function. Okay, so now let's see what happens, and let's just write out the answer in full. We're once again going to use our Green's theorem that just comes from the divergence theorem. So this is entirely general. That's equals to the right-hand side. So I've done no restrictions here. And what I'm now going to do is I'm going to substitute all these conditions for the Green's function of the Neumann condition, with the Neumann boundary conditions in here, and work out the implications. So the right-hand side is we still have the source term g times the Green's function minus u times our new definition for our Green's function. In other words, we have the delta function minus 1 over the area of D, okay, integrated over the whole domain. And that is then equals to, we have that we've chosen our Green's function derivative to be 0, so it's equals to just the first term. And so if we know G2, the right-hand side over here is well defined because we are specifying du dn. And now let's just simplify this little dude a little bit. So there we have basically this delta function will give you u, and I'm going to multiply through with a minus. So we're going to have u is equals to the minus, then take it to the other side. So it's positive, g2g ds, okay. And what I'm going to have is minus, because I'm just going too fast. Because I multiplied through by a minus, so it's minus that term coming in, plus this thing, which is basically the integral of u ds prime over the area of D, okay, and you could say, how can this be, because we don't know what u is, but the fact is we don't care, okay. So this gray term is the average value of u, because it's the integral of u over the area of the integral, and that's the average value of u. And remember, we've got uniqueness on u only up to a constant, so we're gonna have to deal with the fact that u is not determined up to a constant. And so we can ignore this term and just remember it always. So we don't actually need to know u what this is because it's not determined. It's very clever. So the term, this thing is a constant, but it is the average value of u, and it can be ignored since u is only determined up to a constant. Okay, so we now have a unique definition for our Green's function, okay, because there we fix the constant, but we can then use that unique definition for the Green's function to determine u up to the constant that is, but we'll always have an arbitrary constant. So it's very clever, but it gets rid of this term. So we basically have, in the Neumann case, that this is the solution. Okay, so that basically gives you the Green's functions for Laplace's equation. You can actually do exactly, if you look at the derivation, you can actually do exactly a similar thing if you had a wave equation or if you had, in fact, a heat equation, and we'll do it later on. And this was also the power of Green's approach, is that the same method that actually worked for all types of equations. And we'll actually examine the Green's functions, because the Green's functions themselves actually gives you an idea of the properties of the solution. Especially when we see the heat equation, you have a Green's function that behaves like a heat source, a point heat source. Here it's sort of, you can have the heat function, the diffusion, the Green's function behaving like the point charge source. So it actually captures something intrinsic about the solutions. Okay, so I want to give you one property of the Green's function, which is the symmetries, and I'm going to basically derive that, and because that's also useful. It's useful not only for using the Green's function, but also when you're deriving one to actually check you've got the right one. Okay, so the symmetry of the Green's function actually works as followed. It says, consider a Green's function, and we're going to evaluate it at two different field points. Okay, so let's write it down. So the first field point is going to be at x0, and then here you have your source point that's still arbitrary. And you're going to have a second Green's function that you're going to evaluate, and I'm going to call it G1, at a different field point with the same arbitrary source points. And then what you do is basically use the identity for Green's equations that we did in lecture 11, but you're going to apply it to f and g. We're now choosing f and g to be these Green's functions evaluated at the two different source points. And so there it is. What we're going to get is basically this right-hand side, and you'll just recognize it as the divergence theorem. So you're going to have the source point or the field point at 0 with a Laplace applied to the field point at 1 minus the Green's function at the field point 1, evaluate the field point 1 times the Laplace on the source point evaluated at field point 0. And then it's also just equals to this expression, okay? And I'm going to call this guy the left-hand side over here, and this other guy the right-hand side, just for notation. Okay, so now for the two cases, the Neumann, the Dirichlet and the Robin boundary conditions, we had that the Green's function obeyed this equation, okay? The Green's function at the field point 0 obeyed that equation, and the Green's function at the field point 1 obeyed that equation, and we're now going to take that and substitute it in here. Okay, so our left-hand side basically becomes this thing, and the delta function just allows us to replace because we're integrating over the source points, simply allows us to replace the source points with whatever coordinates we have chosen here, R1 and R2. And so we have that. Okay, so the left-hand side now simply becomes the difference between the Green's functions where you swap the coordinates around. You've swapped the field and the source points around. And on the boundary condition, if you're dealing with Dirichlet boundary conditions, we know that both of them are 0, so immediately that term vanishes. If we are dealing with Robin boundary conditions, you're going to have that these things are 0, and you can also substitute this equation for each. You basically can change the expression for the derivative of 1 in there and express that in terms of mu g1 minus, and you can substitute, the 1 goes there and the 0 goes there, and then you just have the two identical terms cancelling each other so that you have the boundary term is basically 0. Okay, so there's always the symmetry property in these two Greens, in the Neumann, in the Dirichlet and the Robin boundary conditions that results from applying basically the divergence theorem that we derived in lecture 11 to the Green's functions evaluated at different field points. Okay, for the Neumann case, you have to do a little bit more work, but the result also follows almost straightforwardly. Basically, the boundary term on C is now equals to 0 because both of the Green's functions are normal derivative is exactly 0, so the right-hand side cancels out, and the term that actually has the Laplacian in, we're now going to replace with the definition of the Green's function for Neumann boundary conditions. So we've added this 1 over area, or subtracted this 1 over area term in, and you do the same thing for both of them, and you now substitute this back into what we call the left-hand side, and you're basically left with the fact, and in addition you have this condition, okay, the average, and this is why in some sense that was chosen as the restricting condition, because it just makes basically makes the symmetry property valid for all three Green's functions. Okay, so now we're going to use all those conditions to evaluate the right-hand side. Here's the Laplacian of the Green's function. So we substitute this delta function minus the area in there. We substitute, in there for the 0 and that one in there for the 1. And we're basically left with that expression, and the 1 over area of D is a constant. So when we have the Green's function going to this, you simply have that case where the average is 0. And where you have that one going, multiplying the area part, that's also just chosen to be 0. And so we once again left with these Green's functions evaluated at the one field point, multiplied with a delta function that spikes at the other field point. And you again get this expression. Okay, and that's equals to 0. So the symmetry property holds for the Neumann boundary conditions as well, provided you have chosen this G2, the average value of the Neumann. You've followed very carefully what the definition of the Neumann Green's function is. Okay, and so we're left with that, proving the symmetry property in the Neumann case, and that's about it. Right. So I think that's the end of the lecture 13 that I prepared. It's a quickie. What I can do is I can start on the next one. Shall I do that? Because so your test is on next week, Wednesday. And I'm hoping maybe if I can do the next one now, I can finish the material for the lecture on Tuesday, and then it's done. Okay, and then just the other organizational thing, the work for the test is up to what we do to the end of tomorrow. So we're going to do 2 examples of Green's functions, and it's up to there. Okay, so let me stop this.